questions. We're going to jump right in with Dr. Brewer right now and get into some of the qualities and properties of biochar. And I really appreciate having Catie as part of the team because she's an engineer, and engineers have to do the math. And so I kind of previewed her slides. She's got a great way of sharing this information. So Catie, you're up. Thank you so much for being with us.
All right, well, you said math. You don't need to scare everybody right away. I promise I don't think I have a single equation in these slides. It took a lot of effort, but I think I kept them out. So for those who haven't met me, my name is Catherine Brewer. I do go by Catie for short. I teach in chemical and materials engineering at New Mexico State University. I've been here now for about 8 years. I've been working in biochar since about 2008. I did this as my graduate work on biochar characterization. And so I had to really restrain myself because I knew that I was between people and lunch. And so I'll try to keep this short, primarily to focus on some of the things you may have heard, and then how those connect to the types of things that we measure in a research setting. And so let me make sure my slides are working. So general definition of biochar, this comes from the International Biochar Initiative, and that's a solid material obtained from the carbonization, thermochemical conversion of biomass in an oxygen-limited environment. And they go into some more details that I have here. The key things when it comes to quality are these ideas of what did you start with? So this is biomass, and I'm going to talk about clean biomass. Limited supply of oxygen. If you want to control the quality, you need to control the combustion and the decomposition processes, and that has to do with the supply of oxygen, and relatively low temperatures. I work in Celsius. I know a little bit about Fahrenheit, but I have to do the mental conversion. And the chars that I work with are primarily on the lower temperature ranges, rather into these much higher temperature, kind of more gasification side. And something that I wanted to talk about was also the definition of biochar. And I'll talk about some of these words. When I think about the word biochar, I tend to mean it for something that's used as a soil amendment. There are many applications of chars. And when I say biochar, I'm thinking of soil. And so the way that my work got started is I was a chemist who was joining a group of chemical and mechanical engineers who were building new kinds of thermochemical conversion methods. And those included gasifiers and fast pyrolyzers. And the conventional wisdom at the time was that high quality char could only come from slow pyrolysis. And we didn't do any slow pyrolysis, we only did these other techniques. And my thought was, well, are they actually good chars or not? And if so, good for what? And that was my task. And so I started with this idea of how do we use char? And I've grouped it into 3 bunches. One of them is fuel. So combustion, heat, power, gasification, where reducing carbon monoxide and hydrogen. It's used as a sorbent, water purification, gas purification, remediation of sites that may have heavy metals or other organic contaminants. And then what we call biochar, where it's used for carbon sequestration or to improve the properties of a soil. And so I'm going to talk a little bit about what biochar quality means for each of these uses of biochar. So first of all, biochar, or char as a fuel. And this is where charcoal comes in. And so as a fuel, here are the things that you want from a fuel. You want higher energy density. The whole point is to produce energy. And so you don't want to carry around a lot of material to get that energy. You want something that ignites and burns cleanly. You want something that's safe to handle, so it only burns where you want it to burn. You want something that's easy to grind. I'm thinking in terms of power production. If you're going to put these into blast furnaces, you want to be able to grind it down. And of course, you want something that's inexpensive. And so what are all the ways that we can measure these things? And I threw up a whole bunch of words. I'm not going to talk about each one, but these are some of the things that you'll see when you're talking about char as a fuel. In particular, these higher heating values, the friability, that's how easily it grinds apart. Moisture and ash content relate to things that are in the material that don't give you any energy value. They're along for the ride. And so we need to know how much that is and particle size. So here you've got some equipment that we use to measure the qualities of char related to its use as a fuel. In the upper left, you can see a bomb calorimeter. What we do is we put a whole bunch of samples in this container, we pump it full of 30 atmospheres of pure oxygen, and we light a spark. And then surrounding that is a tank of water, and we track the temperature change of the water. And that tells us how much energy was in the material. We also look at how much of our material is burnable. And so we do a lot of things with furnaces. You can see here, we've got some crucibles in a furnace, we've got a scale. Here's a higher tech version of that. This is a thermogravimetric analyzer. So you can see with tiny little pans, those sit on a balance. We've got a little furnace that goes around it. And we're looking at, if we heat it, how much moisture comes off. If we keep heating it under oxygen, how much ash is left over. And that tells us how much carbon we had to burn as our fuel. Then we get into density. There's a lot of confusion about what's meant by density because it's all one word, but it can mean different things. And so it's mass over volume. Okay, I guess I do have one equation, but it's pictures. We've got bulk density, just fill a container and how much does it weigh? Then we look at envelope density. What is the volume of the particles themselves? And skeletal density is looking at what is included in the void spaces within the particles, so these porous materials. When it comes to particle size, we have ye old sieves down here to screen particles to different sizes. And I want to draw your attention to what's in the bottom right-hand corner. And that is this symbol right here. And this has to do with flammable solids and this idea of how much do we have to cool it down and how much do we have to quench it. When I first tried to ship char samples to other people in the country, my safety people at the university got really nervous because char, when they looked it up in their book, was counted as a self-heating solid. When you put char through a pyrolyzer, you're driving off the oxygen that's around the surface and you're removing many of the oxygen functional groups from the surface. And so when they come out of the reactor, all of the oxygen in the air is now going to go back and react to that surface, which will create these tiny little combustion reactions, which will produce a little bit of heat. And so if your char isn't cool and you expose it to air, you've seen it warm up, or even if it was cool and you expose fresh char to air, you can see it warm up. And so this is where you want to give a chance for that surface to oxidize, to build up that layer of oxygenated groups again, so that it doesn't start on fire where you don't want it, such as in the semi-truck on the way to where you're going to use it. And so you want to look up self-heating solids, are the series of tests from the Department of Transportation for char safety. All right, so that's a fuel. Then we go on to the other one, char is a sorbent. And I put activated carbon here. This is sort of a misnomer because activated carbon refers to something that's gone through two processes. It's gone through pyrolysis, and then it's gone through a separate activation step to increase surface area and change the surface properties. But because they're used the same way, because they're used as a sorbent, most of the quality indicators would be similar quality indicators that you would have for an activated carbon. And so char is a sorbent. Well, what do you want if you're going to use a sorbent? You want a high surface area. You want a surface chemistry that matches the thing you're trying to absorb. You want a high capacity and selectivity. So you want it to absorb a lot of the material. And selectivity, you want it to absorb the material of interest without absorbing everything else. You want fast separation because you don't want a lot of contact time. You want this absorption to happen fast. And like everything else, you want it to be inexpensive. And so if you're going to be measuring the quality of char as a sorbent, we care about its surface area, which is related to its porosity and its pore size. We care about its equilibrium capacity, the surface functionality. Isotherm, they're down in the bottom right. That word means constant temperature. And this refers to checking the absorption capacity at different concentrations, all done at the same temperature. And that's why you keep saying that thing about isotherm. And that just means you're not heating it or cooling it during the analysis. And then particle size, friability. When you're packing these materials into an absorption column, you have to make sure that they are stable enough so that they don't crack down into powder. So you need the right size going in for flow through the column, but also that they don't break down underneath the pressure and the flow of the fluid. Pore size. The tricky thing about pore size is different pore sizes have different functions, which you can see kind of at the top here. You've got the size of, we've got the biggest pores over on the left, the smallest pores over on the right, and they each relate to different niches within biology. So the bacteria, the plant cells, and the size of the pore determines how tightly water is held. So plant available water relates to pore size. And then the smallest pore sizes, these are on the nanometer scale, tend to refer to chemical sorption. And what we found when we tried to answer questions about porosity is that our measurement techniques didn't all measure the same size of pores. And so people would try to use something like nitrogen sorption, which is for the smaller stuff, and they'd be trying to use it to describe plant available water. And you see that there's not a match in the pore size. And so I spent my time at Rice was spent trying to match the ways of measuring pore size with the function we expected those pore sizes to have within char. And so that's something to keep in mind when you get measurements related to pore size, is what is the purpose, what is the connection you're trying to make for its function. And how some things that we measure it. So over here, you can see this is gas sorption, so different types of isotherms. You keep the same temperature, you increase the gas pressure, that's relative pressure here, and you see how much absorbs. You get different shapes of these curves as you increase and decrease pressure, and the different shapes refer to what types of pores are present and what size of pores, much detail that I'm not going to go into. This is what that instrument looks like. This is a gas sorption analyzer, and your sample goes inside these little glass bulbs here. You have a heater that goes around it to maintain that constant temperature, to maintain the isotherm. This is if you're trying to prep it or do an isotherm at a higher temperature. You want to get off all the gases that were absorbed. Then you move your cylinder over to, these are dewars. These often contain liquid nitrogen. And much of our measurement of gas sorption isotherms happen at liquid nitrogen temperatures. So they hang out in the liquid nitrogen bath or ice bath or whichever temperature you're doing. And then you pump in doses of different gases and see how much absorbs based on what you know got pumped in. So that's how we measure these things. And it can go from very simple of BET surface area all the way up to very complex analyses of isotherms. One of the applications that we're doing in my lab is using char to purify gases, in particular to remove hydrogen sulfide gas from several streams. That's the rotten egg smell. And so we've studied how to make char pellets, because the different size pellets determine what size of column you use for gas flow. Those go into columns like this. And then you can see we have our hydrogen sulfide gases. The gas gets conditioned, goes to the column, and then we measure it on a detector. And so if you're looking to measure it as a sorbent for gases, you'll do things like this. You'll look at gas sorption of nitrogen and carbon dioxide, and then the gas of interest. So that's what this looks like. We can also look at surface chemistry. So these graphs over here, these are infrared spectroscopy graphs, and they show how surface chemistry changes with different conditions. And so you can see fast pyrolysis, we keep a lot more of the structures that were there from the biomass. You heat it up more under slow pyrolysis conditions, more of the oxygen groups get pushed off. Gasification, you burned off most of the surface functionality. So you can get characteristics like this. When you're doing liquid adsorption, so you're removing contaminants from a liquid, we start by equilibrium shakers. So we put them on the shaker table for 24 hours, 48 hours, 3 hours, whichever, and track the change in concentration. And then eventually we use that data to build flow-through columns where we're going to pump liquid through the column and track how the concentration changes. And so these are ways that you measure char as a sorbent. Same material, but use different measurements to determine if it's good for that use. All right, carbon sequestration. So if it's going to act as a carbon sink or carbon storage, what do we want? Well, we want a material that has high carbon content. We want that to be carbon that doesn't easily get eaten by microbes and turned into CO2. We want carbon that's resistant to abiotic, so non-biological oxidation, just exposure to air, so similar to rusting or corrosion processes. If we want to make money on carbon sequestration, we need to be able to measure it. And we want our materials, as always, to be inexpensive. And so you'll see these kinds of words thrown around when you're talking about quality for carbon sequestration. A lot of it having to do with the pyrolysis temperatures, the kinetics of these oxidation processes. All will oxidize a little bit. We want to know how much. That relates to carbon stability. We talk about hydrogen to carbon and oxygen to carbon ratios. And this relates to that carbon stability of how much it's been pyrolyzed. Another way to understand carbon stability is to study skeletal density. And that tells you how densely packed the carbon is into these aromatic ring clusters. The bigger the ring clusters, the higher the stability. So all of that, what does that look like? What are some of the measurements? So one of them here, you'll see these Van Krevelen diagrams. And these compare oxygen to carbon ratios to hydrogen to carbon ratios. And how you read these is know that you're starting over in the upper right, and you're trying to get down to the bottom left. So down here at the center, this represents pure carbon, so like graphite. When you start as biomass, you start with about 1 oxygen for every carbon. So you can see grass and wood are on here, about 0.8. And you start about somewhere between 1.5 to 2 hydrogens per carbon. And then as you heat it, these are lower temperature chars, higher temperature chars, up towards graphite. You're moving towards pure carbon, which is going to have the highest stability. And so this is one way of plotting carbon stability for sequestration, is how close are we to this pure carbon landing point. And we just measure this by measuring the hydrogen, carbon, and oxygen content within the char. You also have the stability against biological attack. And so what we did here is we added char to soil with microbes that are present. This one was corn stover, so we added just plain stover. And you can see that the microbes present in the soil loved this. Over 4 weeks or so, they ate up a lot of that carbon and spit it out as CO2. But you can see the chars, and these are made at increasing temperatures, spit out some carbon at first. So some of it's edible to microbes, but not nearly as much. So we can look at what amount of the carbon present is bioavailable. All right, and then char as a soil amendment. What do we want? Well, first of all, understanding the difference between char as a soil amendment to improve soil properties versus char as a fertilizer supplying plant nutrients. And I'm looking to see that I don't have a lot of time left, or I don't have that many slides, but this is something to keep in mind when you're talking to other people, is this difference between what is a soil amendment and what is a fertilizer. They are not interchangeable. And then what things do we want it to do on soil? The best way to measure biochar as its ability to improve soil properties is to measure the soil properties themselves. And so you can try measuring it outside of the soil and get some correlations, but the best measurements are where you add it to the soil and track how the soil changes. Takeaway messages, if you remember nothing else from what I say, is that char is not char. There are no 2 chars that are exactly the same. And so you do have to track changes in quality. It's not just biochar. If you need to determine a high quality char from things you can measure without fancy equipment, the char should be black. It should be consistent. So not a lot of gray, not a lot of brown mixed in. It should never feel greasy. That's a sign of volatiles that have condensed. It shouldn't be smelly. Also another sign of volatiles. Friable means it should be easy to squish and break apart. It should be made from a clean feedstock. Any heavy metals you have in the feedstock are going to end up in the char. And so know what you're starting with. And then tailor your char quality to the application, whether you're going to use it as a fuel, a sorbent, a carbon sequestration agent, or a soil amendment. In the presentation that I'm going to share with Chris to share to other people, I put in some potential pitfalls of making char and char quality. I'm not going to go over these now due to time, but I can go back to them if there are questions. And with that, I'm going to end my presentation with my contact information. You can feel free to reach me here. Email is usually best, depending on how often I'm in the office, and then we can set up time to discuss more. And if you're interested in some of the more recent publications, I can share some of those too. So in interest of not standing between you and lunch, I'm going to end my presentation there and we'll take some questions.
But thank you for your excellent presentation, by the way.
My pleasure. I've been trying to answer some questions in the chat. One of the questions I want to highlight is how much does char quality change depending on the soil chemistry and the soil characteristics? And the answer is a lot. When I was at Iowa State University, which is where I did the graduate work, we had acidic soils because of all the regular fertilization, and the alkaline nature of the char was perfect because they're already applying lime. And so adding char was great. You try that here in the desert where you have a soil pH of 8.5, whichever, adding more alkaline to the soil is not helpful, or adding something with higher salinity is not helpful. And so we have to be careful about overdoing it. It also depends on which crop you're growing. Some crops don't show any response at all. Some show more. Some are more sensitive to pH, some aren't. Some are more sensitive to salinity, some aren't. There's a question earlier about the salts that are in char, especially from these invasive species or even native species that take up salt of saline water that does stay in the char, and that can impact the soils you're putting it on. And so we looked at making char from dairy manure to use here in southern New Mexico. We have lots of dairy manure. And because there's so much salt in some of that dairy manure, either from salt that they're feeding to the cows or just salt that exists in the biomass, we have to be careful of what soils we put that on. We wouldn't want to amend that to a chili field that may be salt sensitive compared to another crop that's a little bit more salt tolerant. And so it really depends on the chemistry of the char and the chemistry of the soil you're putting it on. Those two do have to be matched, or at least you need to pay attention to it, lest you try to solve one problem and create another. I think those are the questions that came to mind. One question also was will I share my presentation? So Chris, I sent you the slides. And so if you would make those available to the whole group, I also with my email, if you'd be interested in more of the papers, the manuscripts, if you want some real light reading for a weekend, let me know and I can share some of those papers.
If people go to the website, I do have the speakers' biographies in there. And at the end, I've got some of the resources. And I actually have a link to your research page site, Catie. So they can get right there from that. And I do intend on taking these presentations, and I can include some of the slide shows and put those up as well after the program's over. One thing that interested me when you fell under the gun to speed up there, Catie, was when you started looking at biochar as a soil amendment versus as a fertilizer. And I'm interested in getting that a little bit more because we talk with lots of people. You're the chemist and the engineer, and I hear biochar is recalcitrant, like you said, or we're looking for that recalcitrance, you know, to resistance to breaking down. So that's not always the case, or we just have to be patient because, like you're saying, here we are, New Mexico, Arizona, Utah. We're talking about arid climates and alkaline soils, but we want to do what we can to retain the moisture and build up that biocrust that we were talking about earlier. So just some comments on fertilizer versus amendment.
So soil amendment is the broader umbrella. Fertilizer falls into that category underneath the soil amendment because it's something you're adding to the soil to change or improve its properties. But when I say fertilizer, I'm referring to something that provides plant available nutrients. And a couple of words that are important. Nutrients is it's got to be something the plant needs for growth, needs for function. I'm thinking from an agricultural perspective, but I guess it could also apply to forestry. So this is your nitrogen, your potassium, your phosphorus, some of your micros, so like your iron or your zinc, anything like that. But also the bioavailable. So one of the things with char that we see with nitrogen is there's some nitrogen in char, not a lot, with most biomass we pyrolyze. But what form is that nitrogen? And so one of the tricky things that you can have in desert soils like this is you could have char, or you could have soils that have loads of the nutrients that plants need, but they're in a chemistry form that the plant can't take up. And so some of the nutrients in char are going to be there, but not be available. What plants can get out. Others, some you're going to have to wait over time for that char to oxidize, to break down, to change the chemistry, to change the form of the nutrients for being taken out. And so people ask me, can I just put down char instead of putting down my NPK fertilizer? And the answer is no, because you're not going to have a lot of nitrogen to begin with. You may have some phosphorus, but you've got to check how much of that is available. You're going to also have some potassium, but again, how much of that is available? Now, potassium is usually not too much of a problem in char for being available, but phosphorus and nitrogen can be. And so it's usually you put down the char to improve the soil properties, to improve the soil moisture retention, to give little apartments for all the microbes to live, but you can't just use it to replace fertilizer, especially if you have a crop that needs quite a bit of available nitrogen over the course of a growing cycle.
What about research into mixing that biochar with compost? It seems like that should be a sweet spot.
And that is one of the things I've been wanting to do more research on for several years here. I've been waiting for, well, people keep mentioning the financial part. And so that is something that we want to look into more, especially if we can. One of the projects that we're just starting here is combining composting biochar with hydrothermal liquefaction, which is pressure cooking of, we do wastewater algae, and that creates a aqueous phase that has a lot of the nitrogen left over from the algae. And we want to use that as the water source for compost. The problem is it also contains a whole bunch of organics that would otherwise poison new growth of algae. But we're hoping that the microbes that are in the compost can manage it. And adding char to that would just add more of this stable carbon, these nice porous structures to improve aeration, water management. And so to us, the perfect combination is you'll have the usual plant residues, manures, whichever they're going to go into the compost. You add the char, you add the aqueous phase from hydrothermal liquefaction, and ideally you'll get the perfect mix to recover all the properties without wasting anything. And so that's something that we're going to be looking at in the next few years.
That is really cool. Kelby makes some comments. She said, your presentation was great for clarifying definitions. I actually appreciated that as well too. And then she asked something about your plots. And so, and here she calls it a Van Crevelant, so go right over my head here. Can't you get the same info from a H ratio to carbon, or why do you need an oxygen to carbon ratio as well? So,
and I responded. So the Van Crevelant plot was that picture of hydrogen to carbon ratio versus oxygen to carbon ratio and how close we're getting towards the origin. You can get a good proxy from that by just looking at hydrogen to carbon. I like to look at oxygen to carbon because some of the materials that I work with are not just biomass. I also want to look at how does oxidation change as it's going to affect the surface chemistry. So as a chemist, I want as much data as I possibly can, even if it's going to be overkill for most people's purposes. So H to C ratio, you're right, is going to give you a lot of the information that you need. O to C ratio can add to that to help you understand what types of compounds are reacting and what's left.
And thank you again for our presenters and to you for sharing with us. Look forward for people coming back this afternoon for our virtual field trip and tomorrow morning where we'll get more into the projects and economics of it. So we'll have Nate back, and thank you so much.